So in terms of energy, now in lots of systems, there are multiple types of energy going on. And the key thing for linear momentum, the key energy that we're always interested in is kinetic here. So our definitions of elastic and inelastic collisions are always focused on kinetic energy. So for an elastic collision, kinetic energy is conserved during a collision. And therefore, for an inelastic, obviously, kinetic energy must not be conserved. So I've left a small gap for us to look at some examples of when we'd expect to see elastic and inelastic and sort of what happens. And now just before I fill in those gaps, the way I'd remember it, because it's not always the most obvious which one's which, I just sort of had a little, what's the word? Is it acronym? So the IN, I used to just remember that it stood for is not. So in inelastic, kinetic energy is not conserved. I don't know if you've got your own way of remembering it. Some people just sort of remember that elastic, actually, I can't remember what people, that I had a student who used to remember something about elastic, but that never really made sense to me. But I think whatever way you can do to memorize one of them, then that's fine. Okay. So for elastic collisions, they normally happen on a molecular level. I mean, think back or think forwards to what we're going to cover quickly afterwards. Our ideal gas. So ideal gases, we assume, have elastic collisions. And gases are just made up of loads of different molecules. And generally what happens is one molecule gives all its kinetic energy to the other molecule, to another. Now, inelastic, generally, all sorts of normal size collisions, so most collisions. So if you think car crashes, if you think tennis rackets, you always hear something. And so that's the key indicator that we've got an inelastic collision if we hear sound, or if there's some form of thermal energy. Okay. And whatever thermal or sound energy we get, that's going to be the kinetic energy transformed. So if I lose 10 joules of kinetic energy, I know that I must have 10 joules of other energy. So let's look again at a method that I think will always get you the correct answers. So once we've started a collision question, the first part will always get us to find the velocities before and after. So part A, let's say, we'll start with the conservation of momentum. And that will mean that at the end of that question, we should know M and V before and after. Now, part B will ask us to determine which type of collision we've got. So what we do then is for each object, both before and after, we're just going to find half mv squared. Then we're going to add together your initial and compare to after. And if they're the same, then we have elastic. If they're not the same, then we have inelastic. And remember, inelastic doesn't necessarily mean that they have to have lost kinetic energy. In lots of collisions, so in the term collision, we also class explosions. So if something explodes, it may start with 0 kinetic energy and gain kinetic energy. That would still be classed as an inelastic collision because the kinetic energy hasn't been conserved. In the definition of elastic and inelastic, it never says that it always has to go down for an inelastic collision. We just know it's not the same. Another good thing to always have in the top of your head is think about for inelastic, where has the energy gone? And most of the time, it will just be a descriptive question. So it'll say, where has the lost kinetic energy gone? Sometimes it may be a calculation question. So think about some of the other formulae that you have. So we'll see later, Q equals mc delta T. Now this describes thermal energy. So if we know that energy is lost as heat, this could be an equation we're going to use. But we'll look more closely at that when we actually get onto thermal physics. So now the key ideas that I want you to really focus on are momentum and energy. And first we need to find if it's elastic, and we do that just by doing loads and loads of half mv squared. We just repeat that over and over. Okay. Again, remember, if things stick together or break apart, our masses may be different before and after the collision, so be careful about that. Now, that really encompasses the theory and methods that I think we're going to need when approaching exam questions. And so what we'll do then is we'll go straight ahead and look at some past paper questions. So these are all taken from recent papers. I've tried not to pick any from May 2016 because I don't know if any of you know, but we're going to do a mock paper together right before the weekend before the exam. So I'm saving all those questions so they're all fresh for us. Okay. So let's look at this question. In the collision between two bodies, Newton's third law. Now I've got only applies if momentum is conserved, only applies if energy is conserved, only applies if both are conserved, and then always applies. Well, I mean, if we look at all of these, there's only one that to me seems like it actually makes sense, because all of these say if momentum is conserved. Well, all the things that we look at in this topic are to do with momentum always being conserved. We know that energy is always conserved. Newton's third law, we saw in the very start, basically proved the conservation of momentum. So whenever we have two objects colliding, we always have one force on one and the opposite force on the other. So this is almost like a definition you should know, that Newton's third law is responsible. It's like that came before momentum. It's always been there. Okay? So there are always equal and opposite forces between two bodies. We don't have to do a calculation for that. That's just something that we can say. So a ball X is moving horizontally and it collides with an identical ball Y that's at rest. The speed it's moving at is v, and what is a possible outcome of the collision? So we don't have any numbers, but let's say that each of these has mass m, because we know they're the same. So we can do the same method that we had before. So initial momentum is equal to mv plus m times 0. So it's just mv. So I know that my answer must have the same momentum. So we can say that the final momentum must be mv. So let's look at some of these options. So let's go into blue before I know my final answer. So for C, well, I've got both masses moving in the same direction with v. So the final, I'll just abbreviate it F because otherwise I'm going to write it loads of time. So I've got mv for x plus mv for y, so that's 2mv. So that's wrong because momentum has not been conserved. For this one, the final momentum is mv plus m, but it's moving in the opposite direction, so it's minus v. So I've got mv subtract mv or 0. So that's wrong as well. Part B, well, if we look between part B and part D, we've got the same thing, but just half v and half v in the opposite direction. So I know this is going to equal 0 as well. So I know that's wrong. Now let's look at this one. The final momentum is m times 0 plus m times v. So it's mv. So going back to red, because now I know what the definite answer is, this one is A. Okay, because this is the only one where the final momentum is equal to the initial momentum. For those of you who are really good at learning definitions and learning information, or if you'd have remembered from what we said about elastic collisions, they happen when something transfers all its energy into another molecule. Well, that's basically what we've got here. We had a ball which transferred all its energy into an initially stationary ball. If we did an equation for determining whether it's elastic, we'd also see that this is an elastic collision, but we're not asked for that in our question. But it's always good to sort of have these things in our mind, especially for paper 2. Finally, an object of mass m is initially at rest. When an impulse I acts on the object, its final kinetic energy is Ek. What is the final kinetic energy when an impulse of 2I acts on an object of mass 2m initially at rest? So these questions always come up, and they're normally the ones that get the worst overall result from all candidates, because they give you lots of information, lots of calculations, and it's not always obvious what you actually need to find. So let's see how I can relate the impulse. Well, I know that impulse is equal to mass, the change in momentum. And I know that the change in momentum is equal to the mv final subtract the mv initial. So I'll put an F for final and an I for initial here. The mass is initially at rest, so the initial velocity is 0. So I know that it's just m times its final velocity. So for the first object, the kinetic energy, well, I know its mass is m and I know its velocity is vf. So the ke is equal to 1/2 times its mass times its velocity squared. Now let's do the same for number 2. So I know that the impulse is still the change in momentum, but now I see that I've got 2I is equal to mass times this final velocity, but the mass here is actually 2m. So I can see that the final velocity of my second thing, well, these 2's are going to cancel. So I end up with something which is 2 times the mass, has the same VF. Okay. So what we did was we applied our knowledge of what an impulse is, which is a change in momentum. We simplified it by saying that if it's initially at rest, it's just the end momentum that we're worried about. And so far we've seen that if I double the impulse, but I've got double the mass, the final velocity doesn't change because these 2's essentially cancel. But now let's look at the kinetic energy. So the kinetic energy of my second object is 1/2 times the mass of the second object times its final velocity squared. So that's going to be 2 times 1/2 mvf squared. Well, I saw that was a kinetic energy before, so it's going to be 2 times Ek. So the answer for here is C. Now, whenever you have a question, now sometimes it's given to you like this, sometimes it asks you for the ratio. I'm sure you've seen these kinds of questions before, and you know that these are much harder than the ones where they just ask you to find something else on its own. Find an expression that's useful to you and see how you can then relate the 2 different objects in terms of, so for us it was the speed first of all, and then the kinetic energy. Once we'd seen that the mass was doubled, but the speed was the same, we applied the kinetic energy formula to both, and the final result we end up with is that because the velocity is the same, it's only the doubling the mass that had the effect on doubling the kinetic energy. So the answer was just 2 times the initial one. Would anyone like me to go through the reasoning for any of the paper 1 questions we've just done? No? Is that for the final example? Me. Okay. So it's not really as such anything cancelling. So if you're asking about the simplification, the change of momentum we said was the final momentum subtract the initial momentum. What was important about the initial momentum was that we know that it starts at rest, which means that the V initial is equal to 0, which means that MV initial is also equal to 0. So we can simplify that the impulse is equal to mass times the final velocity. Okay. So that means that for the second one, I can do the same thing, but because I've got double the impulse and double the mass, I can see that they have the same final velocity. So for both of them, now I know that this has 2m and vf, and this has m and vf. Kinetic energy is just half mass velocity squared. So I can put these symbols into my equation for this one and for this one. And then what I do is if I notice here that this equation is the same as this equation, I can rewrite that, which we're told in the question is EK. So I can rewrite that as EK there. So I get 2EK. So in some questions, we will do some cancelling, but in this one, I prefer to think of this as just substituting. The only bit of cancelling or simplifying was using the fact that we're initially at rest for both of them. Okay, rest, whenever you see rest in a question, it means that almost you can take a rest because one of the velocities is going to be 0, so you can ignore that term. Does that sort of answer your question? Okay, perfect. So let's finish off this first part by looking at a longer question. Oh, there we go. Now, so this was taken from a higher level paper. So like I said, the marks, you may get slightly more marks if you're answering this on standard level, but let's answer it anyway. Every question I always recommend, go in with a highlighter and highlight key things. So O has mass 930. O collides from I from behind, moving along the same straight line. Before the collision, the speed of I is 45 and its mass is 850. After the collision, I and O stick together, move in a straight line, and the speed is 52. So hopefully I've highlighted enough information for me to be able to write out equations for the initial momentum, equations for the final momentum, and then I can do that to find the missing value. So we're trying to find the speed of O immediately before the collision. So let's just call that V for when we're doing our equation. So initial momentum. So I, we've got mass of I, which is 850, times by the velocity of I, which we know is 45, plus, now O has the mass of 930, and its velocity is unknown, so let's just call it V. Our final momentum, let's write in this line so that it's nice and easy to see. So our final momentum, well, they stick together, so the mass is combined. So let's put stick there to remind us. So this is now 850 plus 930, all times by 52. And that answer is, let me just get it on my calculator. So 52 times, that'll be 1780. So that'll be 92560 kilograms meters per second squared. Sorry, kilograms meters per second. So conservation of momentum tells me that this momentum here is the same as this equation I've got here. So I can say that 92560 is equal to 850 times 45 plus 930 times the speed. And if I rearrange this, so subtract this over from the other side, I get 930V is equal to 54310. So V, when I divide by 930, is equal to 58.4. Now let's look at the information I've been given. The least number of significant figures is 2, so I should say that that's 58 meters per second. Okay, so in terms of where the 2 marks are, you would likely get 1 mark for correctly setting up your 2 momentum equations and putting them equal to each other, and you would get 1 mark for getting the correct final answer. Okay, now let's continue on to the next question. Highlighters back out because we may get more useful information. So we're told the duration is 0.45 seconds and we want the average force. So remembering the equation that we had before and the value we got. So we know from our data booklet that the average force is equal to the change in momentum over the change in time. So the change in time we're given, that's 0.45. Now the change in momentum is the final momentum subtract the initial momentum, and we're thinking about O. So like we saw in both the skating example and the last multiple choice question, the change in momentum or the impulse is the final momentum. So that'll be its mass times by its final speed. And even though I wrote 58 as the answer to the last one, it's good not to round on your calculator screen. So, I mean, if I was to show you my calculator screen, it still says 58.39784946. I haven't deleted that yet because I know that I need to use it for next questions. So I got that. And, oh, sorry. That should be its final velocity, shouldn't it? So, the final velocity we knew was 52. It's getting a bit ahead of myself there. Subtract then, it's 930 times by the 58.4. Okay. Oh, straight lines are really difficult on my tablet. And then we divide it by 0.45. So putting that into my calculator, the top part of my equation becomes minus 5950 divided by 0.45, which gives me minus 13222. Again, 2 significant figures have been used in the question, so I'm going to say that's roughly equal to minus 13,000 newtons or 13 kilonewtons. Okay. So let's quickly, before I take questions, let's quickly look at the answers that we've gotten and see if they make sense. Well, the speed of I increased after the collision, which means that O must have been moving fast. Well, O must have been moving faster, one, to increase the speed of I, but also to be able to catch up to I and collide with it, we knew that O must be moving faster. So 58 is a sensible number in terms of being physically possible. And we know that the car O has slowed down from 58 to 52, so there must be some force acting against it in the opposite direction to how it's moving. So the fact that we get a negative answer is good because it shows us that it's acting in the opposite direction to its motion. So both our answers seem like they could be sensible values and they have the correct sign to be physically possible.